assume that your test hasn't taken place yet.
No, not yet.
Okay. So what last things would you like to cover?
I guess let's keep going over what we just did last time.
Okay. Do you have more problems you can give me, or do you want me to do flashcard type stuff? Or
Unfortunately, I don't have any more problems.
I'm sorry, what?
I said, unfortunately, I don't have any more problems.
Okay. I have plenty of problems, but my concern is that the degree of difficulty on my problems are going to be harder than what you're really going to be faced with. Um, because you can take these identity, in other words, you're going to have to do verifying trig identities. Is that correct? Also,
Yeah.
those can get really hard.
Not on the test. She said that we don't have to do that on the test.
Okay. But clearly you have to know your identities. And one of the values of verifying trig identities is it teaches you your identities. So, that being the case, the best thing we can do is to let me give you some identities and have you prove them. Does that sound like a plan?
Yes.
And I just got to find them. Hold on. I have a book here that's about to fall apart. I can barely find a page. Just a second. Proving trig identities. Now, this does not require anything but the problems I'm about to give you do not require sum and difference or double angle. They only require the first two. I mean the first 11, excuse me. Prove that.
Because sine squared x plus cosine squared x equals 1, then it'll be 1 over cosecant, and then that is sine over 1.
All right.
So sine over cosine.
I'm sorry, what?
Would I turn tangent into sine over cosine?
Okay, so we'll make that sine over cosine.
Plus sine times cosine over sine.
Like that, cosine over sine.
And then that sine on the bottom will be sine squared under the cosine.
Hold on. What's the next step? Is it to distribute this, or is it to add these two fractions?
I would add the two fractions.
Well, notice what happens if we distribute. This cosine gets canceled out immediately. In other words, here's what we have. Now, a lot of times doing these verifying is not so much knowing your identities as much as the technique you use. Okay, so that's what we have after we substitute for tangent and cotangent. Now, instead of finding a common denominator, let's multiply. Let's distribute this. What does that leave us with?
Cosine times sine.
Hold on. Do that part. Always cancel. Always, the very first thing you want to look to do is cancel if you can.
So would that just become sine as a cosine's cross?
Yeah. In other words, always take the route that simplifies it the quickest. And that's canceling out that cosine with that cosine. Now, what else we can cancel?
The two sines.
Okay, I don't think this was cosine squared. No, not yet. It isn't. It's that. I made a mistake when I made this second row is the proper. Yeah, the sines cancel, and what are you left?
I think cosine times cosine is cosine squared x.
So in 2 steps, we prove it.
Okay.
Okay. Now, the best thing I can think of to do is to just give you more problems like this. Because in order to solve these, you really need to know your identities. But like I said, these are only going to be your 6 reciprocal identities, your 3 Pythagorean identities, and your 2 quotient identities. It's not going to test you on the sum and difference or the double angle. If you feel like you need problems like that, we'll go do those.
Okay, so what am I saying explain?
First,
what is that? The secant? Negative secant?
No. First step here. First of all, you don't really. We don't want to convert everything to sines and cosines, merely because we don't have any to start with. Okay? If you don't have anything to start with, in other words, if all you see are tangents and secant squareds and stuff like that, well, then the best way to do these is not to convert to sine and cosine. Let's square this. Let's start there. What do you get? Know how to square a binomial term quickly. By quickly, I mean you don't necessarily have to FOIL it. You should know how to square a minus b quantity squared. And then use that to square this.
So 1 minus tangent squared?
No, that's the number one mistake made in algebra. If I have 1 minus x times 1 minus x, it is not 1 minus x squared. It's 1 minus 2x plus x squared. Right?
Sure.
In other words, a minus b squared is a squared minus 2ab plus b squared. Everybody wants to leave that middle term out, but you can't do it. Okay? So if I'm squaring 1 minus tangent x, what is it squared to?
So it would be 1 squared.
Okay, which is 1.
Minus 2 times negative tangent.
Well, the minus takes care of the negative,
Okay.
so that's the middle term. In other words, don't apply two negatives. If we're squaring this, then our middle term has a negative sign in front of it. Plus what?
Tangent squared, negative tangent squared.
No? Well, again,
It'll cancel out. It'll cancel out.
follow this. In other words, you can FOIL it every single time, but what I'm suggesting to you is that you're going to come across this so many times that it's really worth memorizing that. So you don't have to FOIL it every single time. And when you memorize this, it's a squared minus 2ab plus b squared. Well, that translates to 1 minus 2 tan x plus tan squared. Okay?
Okay.
All right. Now, what do you see in that expression that you can replace with a simpler term?
1 minus tangent squared. Secant.
Well, what is 1? In other words, combine those two terms and what do you get?
Secant squared.
Yes. So now we have secant squared x minus 2 tan x. Bingo. We've verified it. So even though your quiz is not on verifying,
It's still good practice.
well, it is, because there's no usage in the real world for verifying trig equations. Somebody invented it as a method to teach people their identities. And it really does a good job, because after you do these for a while, you realize, wow, I know all my identities now. Let me find another one. Yeah, this happens to be a type problem that you get quite a bit when you're doing identities, proving them, and doesn't have a lot to do with memorizing them, but it's still useful. When you see 1 minus something times 1 plus something, what does that remind you of?
Makes me think that it's probably going to be negative.
Well, it's the difference of perfect squares factored. In other words, if I have a squared minus b squared, that always factors into a minus b times a plus b. So the key is when you see that, you can very rapidly multiply them back together again, because you always are going to get that.
Okay.
So I don't have to take the time to FOIL them. So what does 1 minus cosine x times 1 plus cosine x equal? Based on that.
Would I do the middle term thing?
There's no middle term. That's the thing. In other words, when you have 1 minus something times 1 plus something, the middle terms cancel always. And you only have the 1 squared minus the second squared. So the top always is going to turn into that.
1 minus cosine squared?
Yeah. In other words, if I said factor that, that's difference of perfect squares, factors into 1 minus cosine x times 1 plus cosine x. Well, the trick is to recognize it in reverse so that you can put it together quickly. And in trig, this is a really cool identity to end up with, because I can replace it with one term, either that one or that one. What's that one replaced with?
Sine squared x.
And what's this one replaced with?
Cosine squared x.
So in either case, always be on the lookout for this. That's the way you're going to see it most likely. Or even this. In other words, that's this factor. So now I can replace that entire numerator with, and I would typically do it in 2 steps. In other words, I would do this. And then I would replace it with sine squared x over cosine squared x. What's that?
That would be tangent squared x.
And that's what was on our right side all along. Tangent squared x.
Wow.
And while this doesn't have a lot to do with memorizing your trig identities, this comes up a lot when you're verifying trig identities. In fact, if you ever find yourself with just one of them like this, say, and I don't know what would be on the right side, but let's say we have a verifying trig identity. We're going to verify that this equals something else. Well, when I see this, there's no identity for that. Okay? But if I could turn it into 1 minus cosine squared x, I can replace it with sine squared x. So what we end up doing frequently is multiplying top and bottom by the conjugate. You can always multiply top and bottom by the same thing, as all you're doing is multiplying it by 1 when you do that. And now I know that the top is going to turn into 1 minus cosine squared, which is going to turn into sine squared. So this technique is a very common one when you start verifying.
Okay.
Let me find another few here that only involve what you're really focused on right now. Now, in reality, when you have these, you can actually mess with both sides, but they prefer it if you mess only with the more complicated side and make it look like the right side.
Okay. So would I make that a sine squared x?
No. Cosine squared x minus 1 is not sine squared x. 1 minus cosine squared x is sine squared x.
Oh.
So what is that? You're on the right track, but you got to get it exact.
Cosecant?
No. Remember this. A minus b is always equal to the negative of b minus a.
So then that means 1 minus cosine squared x
Is equal to what?
is equal to cosine squared x minus 1.
With a negative sign in front of it. In other words, if I want to rewrite this in the way I want to see it, in other words, I'm looking for 1 minus cosine squared x, right? Because I'm going to be able to replace that with sine squared x. So why don't we stick a negative sign in front of it? Now I can reverse these two terms. That's the same numerator. And it's really worth knowing that, algebraically, that you can do that. Okay, now what can I replace this with?
1 minus cosine squared x.
1 minus cosine squared x is equal to what?
Sine squared x.
Correct. So I'm going to replace that with sine squared x. So this negative sign was very important. That's what got left out the first time. Okay? Well, that's as important as anything else. In other words, if you don't get the sign right on a problem, you're getting it wrong. So you can't drop a negative sign, and they're not going to give you like half credit. Okay. Now I got to turn this. I got to turn this into this. What could I do?
I could split it, I guess.
Okay, by splitting it, I think you mean this. First of all.
Yes, that's what I meant.
Okay. And then what?
Then you would just multiply the negative with one of the signs, which will make it.
In other words, if you really want to split this into two fractions, we can have that part of it, which is that.
Yes.
Times sine x. In other words, so I'm going to replace this minus sine x over cosine with a minus tan x, and I still have my sine x there, and now I've made it look exactly the same.
Correct.
Okay. Since we only have a few minutes left, tell me what this is equal to.
Sine of a plus b.
In other words, if I said, what is the sine of 30 degrees plus 45 degrees?
Oh, okay.
I'm switching gears just because I didn't want to ignore the sum and difference and double angle. Which tends to get ignored when you're doing verifying, because verifying rarely incorporates any of those.
Sine A times, is it sine B?
No.
Or is it cosine B?
Cosine. Remember that the only one that is the same as the one they teach you at first. If I'd have said that, then that's cosine, cosine, sine, sine.
Okay.
Cosine A, cosine B. What's the sign in the middle?
Sine A, sine B.
Well, first of all, what's the plus or minus sign is what I should have said.
Oh, it's different. It's different.
Opposite, okay. And now it's sine A, sine B. In other words, what you need to remember is that there's two cosines and two sines in both of these. But the only one that begins with the same is that one. In other words, that's all you have to remember is it begins with same, opposite sign, the other. And if you remember this one, which is relatively easy to memorize, then you can always figure out that one. What's the rest of this one?
Cosine, no, sine B.
First of all, what's the plus or minus? What's the plus or minus sign?
It's the same, the plus. Then sine B, cosine A.
Okay. That just needs to be the opposite of that, is all.
Okay.
So notice what that gave us the possibility to do is to figure out the sine of 75 degrees, which we don't really, without a calculator, I don't know how to do that. But using the sum and difference, I do, because that's the sine of 30 degrees plus 45 degrees. And when I translate it to that, that's all I have is 30 and 45 degree angles. And I have those memorized. as you do. So this sum and difference is valuable in that it allows you to figure out odd angle. Same with double angle. Now, the sum and difference and the double angle, some of it you need to be able to recognize in reverse. In other words, what is this equal to? Oops, hold on. That's a big difference. Changing that to the same letter.
So 2 sine A and cosine A. Would I look at the unit circle?
It's a double angle. What double angle ends up with this?
Oh, okay. I'm thinking sine. Would I use the sine formula?
What's that equal to? 2 sine A cosine A is the sine of 2A.
Oh, that's what you're looking for. Okay.
Yeah.
Never mind.
Well, my point was is that you need to be able to recognize it if they give you that, because that's what they may give you. They may not say what's the sine of 2A. They may say what's 2 sine A cosine A. In other words, this is one you need to be able to go backwards on, backwards and forwards. Same with cosine of 2x equals, what's the first one?
There's cosine squared minus sine squared.
That's the one you need to go backwards on. The other two, you're probably good just being able to go forwards on them.
Yep. 2 cosine squared x minus 1 and 1 minus 2 sine squared x.
Yeah, I haven't seen too many cases where they give you that and they expect you to convert it to cosine 2x. Okay? I have seen cases where they give you this, though, and they expect you to go backwards on it. But in general, if you can go forwards on these three, you're in good shape. Is that equal to?
Would it be secant?
Is that equal to?
Tangent squared x plus 1.
And finally, what is that equal to?
So tangent squared x minus 1.
Now look at it again.
Would it be plus 1?
The original is this. So all I did was I took the original and I subtracted 1 from both sides. So that leaves cotangent squared x on the other side.
Okay.
Okay?
Yes.
And this is definitely one that you want to know not just backwards and forwards, but all alterations of it. In other words, notice that 1 is also equal to cosecant squared x minus cotangent. We didn't ever do that one. So if you run across that, you can substitute 1 for it. The key is to realize you're looking at something that has a cosecant squared and a cotangent squared. The moment you see that, see if it is an alteration of that identity.
Okay.
Okay? In other words, that would be a good problem, actually, to give you this as cosecant squared of x minus cotangent squared of x. I never have, only because I haven't thought of it. But it's an excellent identity.
Yeah, it seemed tricky, but it makes sense.
Yeah, well, most people would not recognize that as one, even people that are good at trig. But if you're really good at trig, what you would recognize is that we're looking at a cosecant squared and we're looking at a cotangent squared. I know those are connected somehow. Well, if I go back to my original identity, now I can figure out that cosecant minus cotangent is equal to 1. Cosecant squared minus cotangent squared. So
Okay.
that's kind of the trick, is to, whenever you see common flags, know which identity to go back to.
Okay. So what I can do is draw them out just to help me look at them.
Yeah. You always go back to your three main identities, your Pythagorean identities. Know those by heart, and then know that when you see combinations of those same terms, it might just be an algebraic manipulation of that original identity.
Okay.
Taylor,
Thank you.
good
Have a
luck
good
with your
Thanksgiving.
quiz. Have a happy thanks.
Thank you, too. Talk to you later.
Bye-bye.